In this part, we'll look at the W algorithm itself. There's a central notion here, which is that of the close operation. And the close operation is the one that we use to find type schemes. If we have a type T that contains 3 variables and the type environment E, then close of E and T is a type scheme for all A1 up to for all AK. T, where the A's are the 3 type variables in T minus the 3 type variables in E. So an example of that is that if our type environment says that X has the type B to B, then if we close A to A with respect to E, what do we get? Well, A is a 3 type variable in the type, and A is not mentioned in the environment, so if we close A to A, we get for all A to A. So that's the notion of closing the type. The idea is that whenever no assumptions are made about a type variable, it can refer to any type. Now it's time to finally present the W algorithm itself. The W algorithm, W for well typed, takes a type environment and an expression, and what it returns is a substitution and a type, and this is the type of E. Of course, it may also be the case that the algorithm will fail. If we present the algorithm with an expression that cannot be well typed, the algorithm will fail. So this is not quite what we said earlier, that we only return a type, we also return a substitution. The W algorithm will try to build a type derivation for E and small e, and then try to find this T. So it's going to build a type derivation so W is recursive. And the algorithm has a case for every type rule in our type system. I'm going to present them now. And along the way, we present the corresponding type rules. Now, in the algorithm, the W algorithm, we also assume that we have a constant environment, sigma, that assigns type to constants. And we're going to use this in one of the cases. The W algorithm is syntax directed, as we're going to see now. It's syntax directed in the syntax of the expression that we're trying to type. The first case to consider is the case where the expression is a constant, and this is where we need the constant environment. And remember, the algorithm is based on the type rules. So the type rule here says that if the constant environment gives the constant C, the type T, then in type environment E, C has type T. So here the course of the algorithm is return, well, what do we return as the substitution? The identity substitution, there's nothing to say, and the type that we find by looking it up in the constant environment. So that case is quite simple. If our expression is a variable, well, the type rule for variables is a lookup rule. It says that if in the type environment e of x is t, then we know that x has type t. So here the algorithm says, well, there are two cases really. If x is mentioned in the domain of e and e of x is for all a dot 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 for all a k s, then return the identity substitution and the type s. Otherwise, if x is not in the domain of e, then we fail. So these are fairly easy cases. What if our expression is a lambda abstraction, lambda x e1? What then? Well, first let's look at the type rule. The type rule says that if we want to type lambda x e1, then it has type t1 to t2. If it's the case that we, by assuming that x has type t1, can type the body e1 with type t2. Well, what does the algorithm say? Well, it says that, well, let a be a new type variable that we'll need for typing the argument. What do we do then? We run the well-typeness algorithm, W algorithm, on the body E1 in a type environment where we assume that X, the form of parameter, has type A. And suppose what we get is a substitution T and the type of the body. Then what do? Then we return the substitution and an arrow type, which is the type of the argument type. We find that by applying sigma to A, and the result type is T, because T is the type of the body. So that's what we do if we have an abstraction. Next, consider the case where E is an application, E1, E2. What does the type rule look like here? Well, we're talking about a function application. So if we're typing the function application E1, E2, then we require that E1 should have a function type. So let's say that it's the argument type TA, to result type TR, and then E2 should have argument type, and then we require that the type of the application is the result type. So what do we do here? Well, we must find the type of E1. So what we do is that we call the W algorithm on E1. We get back a substitution, sigma 1, and the type of E1, which is D1. And then, now we know the instantiation of the type variables. Then we apply those instantiations to the type environment. So we apply sigma to all the types in E, and then we find the type of E2. We get a new substitution, sigma 2, and the type T2 of E2. and then we must find out what the type of the result is, and to do that we introduce a new type variable. So let A be a new type variable. So what we want for this to all make sense is that the type T1, which is the type of E1, should be an arrow type, T2 to A. So this is the equation that we have to solve. Here we're not talking about T1, but T2 is the type given a substitution sigma 2. So here we should apply sigma 2 to T1, to the type expression T1. And this is the equation we're trying to solve. So we solve this by calling unify on sigma 2 of T1 and T2 to A. Then we return. What do we return? Well, we return a substitution. Unify returned a substitution sigma. So what we do is we take sigma, and then we apply sigma 2 to that, and then we apply sigma 1 to that. So that's our substitution, and the type is sigma applied to A. Well, that's the case if something failed. One of the W calls or unify failed, then we fail. So that's the case for application. Now for pairing. If we're typing a pair E1, E2, well, what do? We try to find the type of E1, we get a substitution sigma 1 to type T1, then we apply the substitution that we have to E and find the type of E2. We get a new substitution sigma 2 and the type T2, and then we return. What do we return? We return sigma 2, but sigma 1 applied to that, and the product type T1, T2. If one of the W calls failed, then we of course fail. Now, the last case is that of local declarations. Now let's consider local declarations. Let X equal E1 in E2. What's the type rule for lets? Well, to type in type environment E, let X equal E1 in E2. What do? Well, first we must type E1, we get some type S, and then we add an assumption about the type of X. And here we close S with respect to S, and then we type E2, and the type T that we get becomes the T of the let expression. So the way we handle this in the W algorithm is that we first call the W algorithm on E1. This corresponds to the first premise of the type rule. We get back a substitution and the type of E1 S1, and then we try to find the type of E2, and we do that in an updated environment, E prime, and E prime is the old environment where X is now bound to close of S1, but remember we know something more about the type, so it's sigma 1 of E and it's sigma 1 of E here. But that's our new type environment that we use for typing E2. We call the W algorithm on this new E prime, and on E2 we find sigma 2 and S2, and then what do? We return S2, and what's the substitution? Well, it's sigma 2 composed with sigma 1. If one of the W calls failed, then we fail. So that's the last case of the W algorithm. What do we know about the W algorithm? There are two very nice results about the W algorithm. One is a theorem of soundness. That's the theorem that says that if we call the W algorithm on E and an expression E, and we get back a substitution sigma and T, then whenever we have that E has type T1, then it's the case that this type T1 is a specialization of the type T. So this means that T is the most general type. So the soundness result says that if we can find a type with the algorithm, it is indeed the most general type that E can have. It's what we call the principal type. The other nice theorem about the W algorithm is a theorem of completeness. It says that if E has the type T according to a type environment E, then actually it's the case that if we call the W algorithm with E and that we get back a substitution and a type T, and it's the same type, or rather, this actually says that if we conclude that E has type T1, then whatever type T1 E may have in the type system, it's a specialization of the type that the W algorithm finds. So the very, very nice result about the W algorithm is that it accurately captures the parametric polymorphism that we have in Haskell. So a natural question to ask is, how fast is the W algorithm? Nobody really knew. Until 1989, everybody thought it was a polynomial time algorithm. But actually, in 1989, Kafuri and Turin and Orchigian showed that the type inference problem is actually X time complete. So it's not a polynomial time algorithm we got, because the underlying decision problem is complete for exponential time, and one can actually find expressions that have principal types that are very, very large. Very, very large. So we're lucky that in most cases the type inference algorithm that Haskell and the ML implementations use actually give us types very fast. There are extreme cases where type inference is slow.